Hi everyone, welcome back to another lecture of COP-3402. Today I'm going to be talking about pipes, job management, and a little bit about terminal multiplexing. So to begin, let's resume where we were working on last time about pipes. So previously I had shown how you can use pipes to connect simple command line tools together to form more complex, sophisticated tools. So for example, we had this pipe here, running the find command and then piping the results to the command grep hello. So let me just demonstrate this in my command line. If I zoom in here and I run find, you can see it prints out all the files that are in my current working directory. So let me run the tree command. You'll see, not current working directory, but my current directory hierarchy. So from the tree command, you can see what files that I have are in this current file tree here. And if I run find, all these results are printed to the terminal. Now what I can do is say run find and then pipe my results to find results, and then I could run grep to grep for the word hello in find results. And that works, but we don't want to have to use an intermediate file, so instead what we can do is use a pipe. So I could say find and then pipe the results immediately to grep hello to obtain the same output as before. And to sort of illustrate this concept, I have this little diagram here prepared. You can think of it like this find command here is on the left-hand side of this pipe, and we are connecting the terminal input, standard in, to find, and the shell does this for us when we start a process. Or I'm sorry, not the shell, but the kernel will do this for us. When we start a process, it will automatically open standard in for us, standard out, and standard error. I've omitted standard error from this slide, or this diagram here, because it's not important. And when we connect these processes or shells, you can think of it like we're changing the first command standard out to be to the right end of this pipe. So each pipe has a right end and a read end. We'll talk more about that later. And we have changed the standard in of the second command to point to the read end of the pipe. And the standard out of the second command remains the terminal output. So you can see it actually forms sort of a pipe-like structure here, a pipeline structure where all the commands connect to each other. And we can do this with more than one command, so I could have like this sequence here, where we're doing our previous command and then piping the results to word count to print the number of lines, words, and bytes in the output. And a word is any contiguous sequence of characters that are not separated by spaces, so that's why we have 3 words here. But I could print out like just -l, for instance, with the -l flag, only print the lines, and you can see we only get lines, so that works. This is just another example. You can run this in your own time. So what exactly are pipes, though? We've been using them. What are they? Well, you can think of them as a virtual file. And by virtual file, I mean they don't actually take up space on your machine. There's no, well, they do, but not permanently. There's no hardware permanently storing the results or their data being stored in these pipes. They are virtual in the sense that you can send data to them like you would any other file, and then read data from them like you would any other file. And again, by file, I really should say file like object. So as we've discussed earlier in this course, there are regular files, directory files, link files, network socket files, block device files, character device files, all sorts of different kinds of files. You can consider pipes as just another kind of file. And this really enables a form of inter-process communication. So that's just a fancy way of saying letting 2 processes talk to each other. Another way that processes can do this is through a concept known as signals, which we'll be talking about later in this lecture. Now I want to demonstrate the xargs command here because it's sometimes very useful when working with pipelines. And by pipelines, I mean a sequence of commands separated by pipes. So what xargs will do is take each line from standard in and turn them into arguments for a given command. So for example, if I want to run the find command here, get all the files in my current file tree, and I pipe this to the file command, so let me actually run file individually first. If I run file on the hello.txt file, you can see it prints out what kind of file this is. But if I were to try and pipe the outputs of find to file, I would get an error because the outputs of file or find as they are is not parsable by file. I think this is partly to do with the \newline characters. So what I can do instead is pipe the outputs of file to xargs, and then pipe this to file hello.txt, or file I should say, sorry. And what this will do, not file, pipe the outputs of the find command to xargs file, and now you'll see that every file in my current directory tree is printed alongside its file command outputs. And you can imagine how using these sorts of pipelines enable us to build rather complex tools. So for example here, we're running the find command to list all the files in my user include directory. Then we're running this grep command to only get files that end in a .h in the .h characters. So this \dot means look for a literal period character. This h means look for the h character, and then this $sign means match this pattern only at the end of the file name. And then we're using xargs here to pass each file name to the head command to print the first 3 lines of text from each file. So let me run this command by itself so you can see what the output is. It's just the names of all the .h files here in my user include directory. And if I run the whole command sequence, you'll see that we actually get the first 3 lines of output from every one of these commands. Our first 3 lines of output from each one of these files that were printed. And when you actually run head like this on multiple files, it will print this nice convenience message of what file each header comes from. And sort of just a fun fact here for your edification, Dr. Zillow does in fact use these sorts of pipelines, and I use them too in our actual research work. So these sorts of pipelines can be useful for analysis, for research, for running scripts, all sorts of things. So they are practically useful. And one thing you can do with bash that's kind of cool is that you can pipe both standard error and standard out to the following command. So if you use a regular pipe, you're only going to redirect standard out to the following command. But if you use the pipe ampersand operator, you'll send both standard out and standard error to the following command. So for example here, if I run grep define /root, I'll receive an error message because my permission is denied because I'm not running this command as root, but I'm trying to access the root directory. If I were to try and pipe this to this command here, grep-i permission, so I'll do a little pipe here. What this -i flag means is insensitive matching. So I'm going to try and grep for the word permission whether or not there is a capital letter. I can actually remove it since I know that there's a capital letter, capital P here. You'll see that we actually don't get a match though, and that's because grep never receives the output of this output here because it was emitted to standard error, not to standard out, and this pipe only connects standard out to grep. So what I can do is append the ampersand operator here, and now suddenly there's a match because both standard error and standard out were redirected to grep's standard in. Also, while I'm talking about pipes, another cool thing that bash allows you to do is actually check the exit codes of individual pipes in a sequence. So this might be a little bit more than you need to know for this course, but I think it's interesting to know. If I were to run this command here again, grep define root and grep permission, the only command that failed in this pipeline was the first command. The second command succeeded. But if I were to run $? You'll see we get a 0. Because I think, as I recall correctly, the exit code of pipelines is the exit code of the entire pipeline, or the last command that ran in the pipeline, I should say. The exit code of just the last command that ran. But if you wanted to get the exit codes of each individual command to check if a single command perhaps failed in your pipeline, the way to do that, and this is a little weird, but bear with me, it's bash syntax. You have to print out the values in the pipe status array. So pipe status, and the way to get all the values at once is to use this weird syntax of putting brackets and then an ampersand or @ sign afterward. And if I echo this out, you'll see we get a 2 and a 0. That's because the first command here, grep define root, exited with code 2, which is an error code. With a second command, grepping for permission, exited with 0, which is success. So not essential for this course, but it's nice to know that you can access the exit codes of individual components in a pipeline if you need to for some reason. Now, for the next point here, I'm going to be talking about job management. So what exactly is a job? Well, the Unix system defines a job as a pipeline of commands, essentially. So usually a job is just a single process, but if you're running a pipeline like we ran previously here, that would also be considered a job. So let's talk more about jobs here. While I'm running a program, let's say I run the program sleep, which lets you send the terminal to sleep for 10 seconds or however many seconds you enter. I'll say 10. Maybe I'll say 5. What this will do is wait 5 seconds before letting me type commands back to the terminal again. So you can see 5 seconds have elapsed, and now I can type stuff in the terminal again. But if I were to press Control-C while this is running, that will send the sig term signal to the sleep command. And what a signal is a software interrupt. It lets you send messages to processes while they are running. So pressing Control-C while a process is running typically sends it will send the sig term signal, which tells a process to stop running. Now, I'll talk about this more later. Some processes can ignore this signal, but for us, for most cases, when you're running a command from the command line, you can just press Control-C and it will end the process. But there's more we can do besides just ending processes or killing them. We can also stop or suspend them. So I'm going to say the word suspend because killing and stopping sound too similar, so I'm going to say suspend. Control-Z will suspend a process. So if I were to run sleep with, let's say, 30 seconds here and then press Control-Z, it will suspend the process. So the time that sleep needs to finish is not changed. It's not running right now. It's just waiting for me to resume it. Now, you might wonder, okay, if we stop the job, how can we actually resume it? And the way to do this is with the fg command. And this isn't actually a command. It's actually a shell built in. So if I type in help fg, maybe I'll type in type first, type -a fg, you'll see that it says it's a shell built in. So to obtain help for fg, we can't use man. If I were to use man, it wouldn't work. And if I were to use which for fg, we actually would get no output. Instead, we have to use the help command. So help fg, and then we can see what it says here, move job to the foreground. We can specify a job number, which in this case would be 1 because that's what the Control-Z printed out here for us. But if we don't enter a number, the shell's notion of the current job is used, and that's going to be the most recent job. So I can just say fg, and now the sleep 30 command has resumed. Let me just check that it's still running. Yeah, no, it's not running yet. It resumed, and I think it finished. I think the way sleep is implemented, it must have actually, because it terminated right away, time must have been elapsing while it was in the background, or maybe somehow it knows that the time has elapsed since when I started it, and now it's in the foreground again. Maybe to give another example of this, if I were to type find and then Control-Z, you'll see I'm getting all the files in my directory hierarchy. If I enter fg here, it goes back to the foreground. So another example, perhaps a more illustrative example. So what is this notion of foreground versus background? What does it actually mean? Well, foreground just means the shell is running, the process is running over the shell, and the background means it's running separately from the shell, detached from the shell. Foreground processes prevent you from entering additional commands, but you can send signals to them. In the background, you cannot send, they don't block your terminal output, terminal input, but they will redirect output still to the terminal, and you cannot send signals to them. No Control-C for terminating them, and no Control-Z for suspending them. Let's see what this looks like. We could run the sleep command here with time, let's say 10, and then I could say Control-Z to suspend this process, BG to run it in the background, so now it's actually running in the background. And Control-C, as you can see, will not terminate it because it's not running. However, because I pressed a command here, here's one more thing I guess I should mention. When a command finishes, bash will not immediately print that it's done to the terminal. Bash will wait for you to enter some sort of input, and then it will print that out to the terminal that the command is finished. And there's another way to put processes in the background. So this is the first way. I just want to reiterate. You can start a process, press Control-Z, and then type in BG to send it to the background. That's the first way to send a process to the background. Here I'm typing FG, and you'll see we're waiting again for the sleep command to finish. The second way is to be able to skip pressing Control Z and then BG, and then entering BG. You can also just add the ampersand here to put a process immediately to the background. So I could say sleep 2 with ampersand, and that immediately goes to the background. And then if I just press enter a few times, once it's done, the shell will print that it's done to the terminal. But for example, if I were to run a command like cat, which cat normally expects user input, press Control D to terminate the input there. If I run cat in the background and then enter the jobs command to look at my currently running jobs, you can see cat is still suspended, and it's expecting more input. I can bring it to the foreground with FG, press Control Z to suspend it again, and then background can actually send it to the background again. But again, because cat expects input, it's not actually going to be doing anything while it's in the background. I can put this back to the foreground now with FG and then Control D to end the input and kill the job. So here's an example of running multiple jobs. I'm going to run the sleep command in the background for 1 minute, the cat command in the background, and the command grep hello in the background. And grep hello, that's the pattern, but we have not passed input to grep, so it's going to be waiting for input. And then I'm going to run the jobs command to view all the jobs that I currently have pending. You can see we have all these jobs in the background right now. I think that sleep command, yeah, that one's still running. And we run the jobs command again. You can see, yeah, the sleep command is still running in the background because that one does not rely on user input. It's actually running in the background. These commands are waiting. And I can bring up a specific command by typing in its number. So I could say FG2 to bring the cat command to the foreground. So hello world, and it's in the foreground. Press Control D to terminate the input. Now if I enter the jobs command again, oops. Sleep 1 minute is still running. I'll bring that to the foreground. FG1, Control C to kill that job. And then I can just say FG to bring the last job to the foreground, Control D to end the input, and then end all those jobs. So you might be wondering, how do we actually kill a process that's in the background? Well, we could bring it to the foreground and then press Control C. That's a little more manual work though, and it's kind of annoying. And the even worse reason here why you wouldn't want to do that is because Control C may not even work. Some programs, they can ignore the sig term, the terminal signal sent by Control C. The better way to do it is by sending the sig kill signal, which cannot be ignored. That definitely kills a program. So for instance here, if I say sleep for 1 minute, and then enter the PS command to view running processes, you can see sleep is running. I can see its PID here. I'll copy that, and then the kill command expects a PID, 9908. We'll pass that to pass the PID of the sleep command to kill, and then you can see it says that it terminated sleep. Now, you might be wondering, okay, what is this -9 for? This in the slide here. Well, the -9 is to specify the actual signal we want to send to a command. So the kill command on its own actually by default sends the terminal signal. It doesn't send kill. It sends sig term. And really, kill is used for sending all sorts of signals. It's kind of poorly named. It just lets you send any signal you want to an existing process. So to actually kill a process, you have to pass the signal number 9, which is the kill signal. So again, if let me do this process here again, see that the sleep command is running. We have the process ID here, 9925, kill, -9, sleep. Or not sleep, 9925. And now that process has been killed. Before it said terminated, now it's actually been killed. And one more, I guess, thing that you don't need to know for this class necessarily, but is useful to know, is the pkill command. So pkill is different from kill in that you can pass it the name of a command instead of the PID. So if I type in sleep again here for 1 minute, and then run in the background, I can run pkill -9 sleep, and that will actually find the command with the name sleep and kill it. And you can see it actually works. So you don't need to memorize the process names. You can just type in the name of the command and kill it with pkill. If you're curious about all the different signals that are available for you to send to processes with kill, you type in man7 signal and you can see them all. And you'll want to scroll down to there's a table here, not this one, right here. Signal numbering for standard signals. I'm on an x86 machine, so for me, sigkill is number 9. And it is that for all machines, but for me it's definitely number 9 because I'm on x86. And this process management lets us get a sort of quick and dirty development workflow here. I'm going to show an even better one later, but this one actually works for a good amount of editing jobs. Let's say we have a file we're working on in Vim. So I have one here, hello.c. Main.c, I should say. Let's say I want to edit this file or run this file. I can press Ctrl Z to go to the background, then run GCC to compile it, and then I can run a.out to actually run this program, or main.out to actually run this program, or run main. And now, instead of reopening Vim, which might send me back to the beginning line of my program and require me to navigate all the way back to where I was working on to continue editing it, I can just enter the FG command, resume editing where I was, then Control Z to go back to the background, and then run these two commands, the compile command and then running command in sequence. Now I'm going to resume that process again and kill it properly this time by using the :Q command. So this development workflow of using processes to send your compiler, or your editor I should say, to the background and then putting it back to the foreground when you're ready for editing again is a decent workflow for editing, but a better workflow involves using terminal multiplexers. And multiplexers, they enable you to split your terminal into multiple panes, multiple tabs, even connect to remote desktops and detach from those remote desktops to let them keep running in the background, all sorts of things. The one that you'll probably be using on Eustace, you might be using is Biobu, but the one that I like to use is called Tmux. It's a more traditional terminal multiplexer. I think Eustace actually has Tmux available on it as well. I'm not going to go through all these slides here, but one thing I will bring up is that if you run a long-running process on Eustace while you're in Biobu, you can actually press one of these commands here, the detach command, to go back to your remote machine, your host machine, but leave that terminal instance running on Eustace on the remote machine. So you can actually have a really long compile job running while you're not even on that machine. So to sort of demonstrate what this workflow looks like, I can enter Tmux on my shell here to actually enter Tmux. And if you've been to any of the class lectures, you've already seen me do this by now. Now I can press a hotkey to split my window into two different panes. So for me, it's going to be Control space and then %. But for you, if you're just installing Tmux for the first time, it would be Control B. So Control B %, for me, Control space %. And that will do a vertical split. So my terminal window is split in two, and I can navigate between these two windows. And now I can open up that main.c file I was working on earlier, and I can make my changes here on the left-hand side, flip back over to the right-hand side, and then run my compile command, gcc-o main, main.c, and then /main. And I can easily navigate between these two panes to make changes and then recompile my code. And I can even do more splits, so I could say Control B double quote to do a horizontal split. For you, it would be Control B. For me, it's Control space. So that's a pretty cool, I think, and effective way to do development. And the way you switch between these two panes here, I'm not sure what the command will be by default on Tmux. I've reconfigured it to match the Vim key bindings of HJK and L. I hold Control and press HJK and L to move between these two panes. But you might have to configure that yourself, and I encourage you to configure your tools to your liking. So that pretty much wraps up the lecture. Just to give a brief summary of what we went over in these past two lectures on processes. Processes are a way to abstract away CPU resources. So you might think we could just run a program by loading it into memory and then moving our program counter to the first command in that first instruction in that program, and then just telling the CPU to do its thing. Well, we could do that, but this doesn't work if you have one CPU or really more programs running than you have CPUs available. Because then you have to wait for one command to finish before you can run another command. The idea of processes enables the operating system to, and you with the shell, to manage when processes are running and sort of provide the illusion that they're all running in parallel. It lets you have, like, again, multiple windows open at the same time. And the way we create processes is sort of like cell mitosis. It's always through duplication. And we duplicate processes in this way by using the fork syscall. And then once processes are duplicated, you, in the child process, would run the exec syscall to replace that child with a new command instead. So only fork creates processes. Exec does not create a process. It replaces an existing process with a different process. And standard I/O, very useful for us. Having these 3 file descriptors open by default on every program enables us to easily create pipelines and redirect the input and output decisions of programs without having to change the source code of those programs themselves. Pipes are useful for letting us connect programs together to create more complex pipelines or complete more complex tasks. We can also use process substitution, but the syntax for pipes is a little bit nicer. And finally, you can use commands like fg, bg, and jobs in conjunction with signals like the signal for stop and the signal for terminating a process, for instance, to manage when processes are running, to put them into the background, let them run in the background without blocking your terminal, or resuming them so that you can view their output or kill them if you don't want to run them anymore. And remember, you can always send a process to the background when you're running it by ending the shell command to run the process, run the program, with an ampersand. So put an ampersand at the end of a command, and that command will run in the background. And that concludes this lecture.